Everybody. Um, all right. I think this is working. Let me know if you have trouble hearing me at any point. Um, the looks like the stream is about maybe like 10 seconds or so behind when I'm talking, so I'll just try to leave some time at the end of sections. Um, all right, great. Yeah, we'll give people about 5 minutes to log in. Yeah, so we'll be doing this through YouTube instead of Zoom. Um, we could use Zoom also. We'll see how this goes. Uh, YouTube gives me a little more control over how stuff gets streamed. I'm also a little bit worried about the number of people using Zoom. But yeah, so we'll see how this YouTube option works. Hi to everybody that's just logged in. Be getting started in just a few minutes. Um, Let me know if you have trouble hearing me at any point. Um, if the stream gets interrupted for any reason, just give me a few minutes to try to get it back online. Um, Looks like everything's going okay so far. Uh, the stream's about 10 seconds or so behind when I'm talking, so I'll just leave some time at the end of sections for questions. Um, yeah, we'll see how this goes. Yeah, feel free to let me know at the end of this uh, how you think this went, doing it this way through YouTube, um, or if there's any way we can make this better. Right, we're going to get started in just a few minutes. Uh, just a reminder that you should be working on the lab, ideally today or tomorrow. The TAs will be available during the normal lab session times. So Celia will be available 4 to 6. Matt and Eve will be available 6 to 8 via Zoom if you have questions. You can also email us outside those times, depending on where you are in the world. Next week, during spring break, there won't be any lectures or lab times or office hour times, but feel free to email me if you want to set up a time to talk via Zoom. Homework 7 is out now and is due 2 days after spring break. So you might want to try to work on it these couple of days before you leave if you haven't left yet, or you can work on it when you get back. There will be office hours that Monday on the 23rd, right when we get back. All right, I think we're going to go ahead and get started. This will be a learning experience for all of us, but again, feel free to use the chat box to ask questions. I'll try to be checking it every couple slides. If I don't see your question, I'll just go back to it. Okay, so today we're going to be talking about the t-test, and um, so this is finally after the last few weeks of talking about probability and the central limit theorem and things like this. We're finally going to get to a practical test that we could actually use and is actually used a lot in psychology. And so the t-test came out of a very practical problem. About 100 years ago, the Guinness brewery was trying to scale up production from a relatively small scale operation up to a much larger quantity of beer. And the problem was that their old approach for figuring out if they were being consistent no longer worked. And their old approach was basically just have a person manually check every single batch. And so um, what they wanted, just quick question, logistics question from Erica is that homework 6, I just pushed back the deadline on courseworks to tomorrow, just so that, because I know people have been very disrupted this week. So as long as you get homework 6 submitted this week, there won't be any late penalties. um, and so, yeah, feel free to, if you wanted more time to work on it, feel free to resubmit before Friday. Okay, so at the Guinness Brewery in 1906, they were trying to come up with a method for figuring out if their batches were being consistent or not. They wanted a way to just sample a small number of batches and then decide if their production process needed to be adjusted or not. And so they hired this statistician, William Gossett, and his job was basically to figure out how few samples you could take from this production process in order to determine if production was drifting away from the values that they wanted. So William Gossett, Guinness decided it was okay for him to publish the work he was doing as long as he didn't reveal that he was working on beer or reveal who he was. And so William Gossett's work was all published under the pseudonym student. And so if you see this referred to as a student's t-test, for example, that's who this is talking about, is William Gossett, who was publishing this beer work but wasn't actually saying he was working on beer. And so, for example, one of the things they wanted to do was make sure that the amount of sugar in their malt extract was very close to this ideal value that they had. They wanted it to be, less than like 0.5% off from this ideal value. And so William Gossett was basically trying to figure out how many samples do we need to take in order to determine and basically test this kind of null hypothesis that the sugar is in this right range. And so the way he actually did it was just by doing simulations. Of course, simulations in 1906 means like writing stuff down on a piece of paper, and it took a very long time. Um, but what he figured out is that uh, when you take these very small sample sizes and try to use um, a normal distribution, it doesn't actually work. And we're going to talk in a couple slides about what the problem is here, right? But he basically realized that you need to he needed to come up with a new distribution in order to explain the kind of results he was getting. So we're going to do some simulations on the slides here, which is sort of similar to what he did. Of course, again, it took him months and months to do this. Nowadays, you could do this in a few seconds in R. So let's run some simulations here. And so the idea is we're going to imagine that we're taking samples from a normal distribution. So the idea here is that we have a population which is a normal distribution centered at 0 with a standard deviation of 5. And we're going to take 4 samples, 4 data points from that distribution to get our sample. And so we get these 4 samples, and what we wanted to do is we wanted to figure out what the distribution of the mean of these samples looks like. And so we talked last week that one thing we could do here is look at how many standard errors away from the mean these sample means are. So the standard error in this case, which we talked about last time, is just taking the population standard deviation divided by the square root of n here, which is 5 divided by the square root of 4. And then we could compute a z-score, which is how many of these standard errors away from the population mean is our sample mean. So we take our sample mean and divide it, and here the population mean is 0, right? So we're just taking our sample mean divided by the standard error. And so we're going to do this many, many times, right? So all we're doing is drawing out 4 values from this population, taking their mean, and then computing a z-score. How far away is this mean in units of standard error? How far away is it from the population mean of 0? And so by the central limit theorem we talked about last time, the sampling distribution of this z-score should look like a standardized normal distribution. And it does. So the gray area here is our sample, is the density that's coming from this sampling. And in black is the sort of ideal normal distribution that's centered at 0 with a standard deviation of 1. And so you can see this approximation is very good. Excuse me. You could get them even closer if you did more and more samples. So this all makes sense, right? This is what we should know from the central limit theorem. And the problem, of course, with actually using this kind of sampling scheme in order to do statistical testing is that it requires us to know the this population standard deviation, right? And so we usually don't know this, right? There's very few cases where we will. And so we don't actually know how to compute the standard error, right, in order to find this distribution for our samples. So what we do know, what we can compute, is a standard deviation from our sample, right? And so what we could do instead is do the exact same thing as before. We're going to take 4 samples from this population. And now we're going to compute the standard error instead of using the true value of 5, which is the true population standard deviation. We're going to compute a standard deviation from our sample, right? So we're putting sample values into this standard deviation function. We're going to try to compute a z-score here. As we'll see in a second, we actually don't call this thing a z-score. But right, we're taking our sample mean divided by the standard error that we computed using our sample standard deviation, and do this a bunch of times. And if we look at this distribution, so in black is the same normal distribution we had before, and in gray is this what's coming out of this simulation. And we can see that it's pretty far off, right? It's the same general shape, sort of, but the tails here are much heavier, right? It's much more likely that we're getting these z-scores that are too big, right? That the normal distribution, for example, says we should almost never get z-scores that are bigger than around 3. And we are very frequently getting z-scores bigger than that. Right. So the problem is that we can't just substitute in our guess about the population standard deviation instead of the real population standard deviation. Um, and so what this means is we can't actually use the kind of z-tests we talked about last week for most practical problems, right? That when we actually try to compute the standard error based on our sample standard deviation, the distribution no longer looks normal. And so um, there's a few times that we will know the population standard deviation. So, for example, sometimes there's measures that we're using that are like defined to have a specific standard deviation, or there's cases where n is so large that our estimate of the sample standard deviation is really close to the population one, and so the fact that it's a guess doesn't matter too much. But this is not really true for a lot of problems, and it wasn't true for this case that William Goswell was working on, that they wanted to be able to do a small number of samples, right? They didn't want to waste a lot of their product in this sampling process. And so trying to use the z-distribution was causing problems that they were incorrect more often than they expected, meaning that if they tried to use their samples to obtain confidence intervals, their confidence intervals were too small. Very often they wouldn't include the actual value of production. I'm sorry, my son has a cold. Okay, so what they came up with instead of this z distribution, is using a t distribution. And so the idea here is that instead of using the actual population standard deviation, which we usually don't know, we're instead going to use this normal distribution. And so, but instead of using the z distribution, we instead have to use something called a t distribution. And so I mentioned this in the distributions class a couple weeks ago, but this t distribution is kind of like a normal distribution, but it has these heavier tails, so we more often get these extreme values. And so this t distribution I'm plotting here, for example, is the one that is the one that corresponds to samples of size 4. As we'll see in a second, this is actually a different distribution for different sizes of samples. So it's still centered at 0. We still have this kind of standard score, although now we're going to call it a t-score instead of a z-score. And it's different in that it has these heavy tails, and that it also is basically a family of distributions that actually depend on the size of the sample. Okay, so the way we actually use this, as I was discussing, is we compute the standard deviation inside our sample. We compute the standard error of the mean using the sample standard deviation. And then we compute a t-score, which is how many of these standard errors away from our population mean we are. Now you might worry about whether we actually know this population mean, which we might not. Often we do, because often the population here we're testing against is going to be some kind of null hypothesis. And so the mean here this population mean is going to be something that we're assuming to be 0, or assuming to be some kind of base rate that we're comparing to. As we'll see, we can also use this same kind of setup to get confidence intervals for the population mean. So yeah, so the mean is either something either we know or we're going to build a confidence interval for. Whereas the population standard deviation is something we usually don't know, right? We can, again, we're estimating it here, but it's usually something we don't know exactly. Okay, let me just pause there for a second if there's any questions. Okay, so so let's do a quick example of this. So um, let's imagining that we're trying to measure these international bitterness units of a beer at the brewery, and we're brewing some test batches, and we're measuring. We just get these four samples, and so in our test batches, we get these four values. And what we want to know is we want to kind of test this null hypothesis. Do we think that these samples are coming from a production process that's producing stouts with a mean of 45 or not? Right? We can see 1 is below and 3 are above. Is this strong evidence that something is going wrong with our production process, or is this just variability around this 45? So to do a t-test, what we're going to do is compute the sample mean, which is just the average of these four numbers. We're then going to compute the sample standard error, which means we compute the standard deviation and then divide by the square root of 4. Our The population that we're comparing to here, again, is 45. That's something we are just assuming as our null hypothesis. And then we compute this t-score, so we're asking how far away are we from the mean relative to the standard error, right? So you can see where the mean is 45, the sample, our population null hypothesis is 45, our sample mean is this 57.65, and standard error is 5.03. So this gives us a t-score of 2.51, right? So we're about 2.5 standard errors away from the mean. And again, the standard errors we're using here is this one we're estimating from the sample, right? We don't actually know if this is the true population standard deviation or not. This is just what we're measuring in our sample. So now if we want to convert this to a p-value, right, what we want to know is how impressive is this t-score of 2.51? Is this something we should be worried about, or is this something that we would expect to see even if the null is actually true? And so if we think about like a z-score, for example, a z-score of 2.5 would be pretty worrying because for z-scores, usually we wouldn't see them over 2 in a null distribution, right? That most of the area of our null distribution for a z-score is less than 2. But in this t-distribution, that's actually not true. So in our t-distribution, this t of 2.51, the central part of the curve here, that's between negative 2.5 and positive 2.5, is actually only about 91% of the area, right? So the p-value here, meaning the fraction of the area under the curve that's out in these tails beyond 2.5, is actually 0.086, right? So in this case, we actually would fail to reject the null hypothesis, right? What we're saying here is that a z-score of 2.5 would be pretty impressive, meaning that something has gone wrong in our production process. But a t-score of 2.5 is less worrying, that these t-scores can sometimes be pretty big, even when the null hypothesis is true. And so a t-score of 2.5 we'd get about 9% of the time, even when our production process is actually centered around the true population. So yeah, there's a question from Alyssa about whether the t-distribution applies for these small sample sizes, which is exactly right. So what we've been showing is examples with only this sample size of 4, where the t-distribution is quite different from the z-distribution. As the sample gets bigger, this is a t-distribution for samples of size 8, here are samples of size 16 and 32, right? And so you can see that as the sample size gets bigger, this t-distribution starts turning into a z-distribution, right? And the intuition for what's happening here is that as n gets large, our sample, our estimate about the standard deviation that we're getting from our sample starts getting really close to the true population standard deviation. And so the fact that we're guessing doesn't actually matter so much. Um, and so there's this sort of like orderly change where these heavy tails are getting smaller and smaller and looking more normal. And so, in fact, if you have an infinitely big sample, the t distribution and the z distribution are exactly the same. Right? So we really only have to worry about this when our sample size is small, and we don't necessarily have a good estimate of what the this population standard deviation is, right? And so again, this sort of depends on the kind of research that we're doing, but it is very often the case in psychology, for example, that we're doing experiments that are closer to this end, right? Maybe we're testing 8 or 16 people or something where there is a noticeable difference. If you're doing experiments with sort of 50 or more data points, then it starts mattering less whether you actually use this t distribution or not. Okay, so the shape of this t distribution, as we were just talking about, depends on the size of our sample. And the statistics terminology we use for this is that it depends on the degrees of freedom. And this degrees of freedom is kind of a general term that has to do with sort of how many like freely moving parts there are in the data, or how many independent dimensions there are in our data. And so we're going to see this in a few different contexts for several of the different statistical tests that we talk about. Um, and so this idea of degrees of freedom is a kind of general concept that applies to a lot of these statistical tests. Um, and so for each of these tests, there's going to be some kind of formula for how we come up with the degrees of freedom. Those will be different for each test. This idea of degrees of freedom is a kind of more general one. And so for this t-test, what matters is the degrees of freedom of a sample mean. And so what degrees of freedom means in this case is that if you know the sample mean of some data set, how much information does that actually give you about the data set, and how much information is there left in the data set that's kind of free to vary? So you can think, for example, let's say I tell you that the mean of two numbers is 3. Um, and then I ask you to tell me what the two numbers are, right? You're not going to be able to do it, right? Because if the mean of two numbers is 3, it could be that the two numbers are like 2 and 4, or maybe they're both 3, or maybe they're 1 and 5, right? Um, the idea is that we know where the numbers are centered, but we don't know how far apart they are. And so if you have 2 data points and you know the mean, then there's this extra degree of freedom, which is that we don't know how far apart those two numbers are. I'm just going to pause for 1 second to answer some more questions. Um, so one question is that is whether if we're using a large sample, does it matter if we use t or z? And the answer is that it doesn't. There's no downside to using the t distribution with large n, and so that's why in practice we will just always use the t distribution, because if you have a small sample, then that's the best choice. If it's a big sample, then it doesn't matter. So you might as well just always use the t distribution. Um, Really, the only disadvantage of the t distribution is that it depends on the sample size, and so it at least used to be when people used to do this by looking up in tables, it was kind of annoying because you'd have to use a different row of the table for every sample size. But nowadays, when you're using R, you might as well just always use a t-test. Um, and then, yeah, there's a question too about how we actually got um, like this area here, and yeah, so there's a bunch of ways to compute this area. You're gonna see several of them in the lab. You could definitely use the integrate function, right? And so here, if we integrate under this t distribution from negative 2.5 to 2.5, there also in R is a dedicated t-test function that does this automatically for you. But that's right. The logic here is exactly the same as the kind of integrations that we were doing under the normal distribution. uh, right? And so um, we're computing the area under the curve. That's right. You can either think about it as computing the central part, or you can think about it, the p-value here is really the area under these tails, right? Then we could compute the area under the two tails and add them together. Yeah, so if you did want to find the area, um, well, so let's see. So yeah, the question is about finding it by hand. So if you mean doing it without a computer, the answer is yes, you can do it using a T table, and that's part of the homework this week is to use a table of T values. Um, if you mean by hand of like integrating it by hand, then yes, I think you'll be doing that in the lab, doing some using like the integrate function. Again, like in practice, if we're actually doing a data analysis, you just use the built-in t-test function that does this integration for you. Uh, yeah, so the integrate function can integrate any density. You have to just plug inside the integrate function. You have to specify what the density is. So far we've been using integrate and then put dnorm inside for density of normal. In the lab today, you're going to do integrate of dt, that's for the density of t distribution. Right. So the integrate function is general purpose, and it can integrate under any distribution. You have to tell it in that first argument of the integrate function what distribution you want. Um, and yeah, and it matters which one it is, right? Because these distributions are different. Okay. All right. No, yeah. Thank you so much for the questions. Feel free to keep them coming. Okay. So I was mentioning this idea of degrees of freedom, right? And so again, for a sample mean, you could think about if I have some data set and I tell you the mean of those numbers, it tells you something about those numbers, but it doesn't tell you everything, right? And so for a sample mean, um, if I tell you the mean of this data set, there's still n minus one things that you kind of don't know. So in the example I was giving, if you have two numbers and I tell you the mean of those two numbers, you sort of know where those numbers are centered, but there's one thing that you don't know, which is how far apart they are. And so this is true for any size of data set that if I tell you the mean of those numbers, there's still kind of n minus one things that you don't know. Another way to think about this is that uh, if I told you the mean of a data set and then I give you n minus one of the data points, you could compute what that last data point is just by knowing the mean and all the other points. And so the degrees of freedom of a sample mean is n minus one. And so um, for example, if we have an n minus four data set, then the degrees of freedom of a sample mean is three. So the reason I bring up this terminology is because this is usually how we talk about these different t distributions. We don't actually talk about them as corresponding to a sample size. We talk about them in terms of their degrees of freedom. Um, and so when we're using a t distribution, we have to tell it, we have to sort of pick which t distribution we're actually talking about by specifying this degrees of freedom, which is just the number of data points minus one. So it might seem kind of silly that we're introducing this whole new concept, which is literally just like n minus one. But this degrees of freedom idea is actually a general thing that's going to come up in other tests as well, and that the formula is not always quite this simple. Right? It's again, it has something to do with sort of how many unknown things there are in the data set. And this is usually how we talk about these families of distributions is in terms of their degrees of freedom. Okay, so let's just to review, go through what this t-test looks like. And this is called a one sample t-test for reasons that'll be clear in a minute. It doesn't mean we're taking a single data point. It means we're dealing with a single population. So the way we derived this test is we made two assumptions. First, we're assuming that the central limit theorem is in play here, meaning that the sampling distribution of the mean is normal, which will be true for any normal population or any population at all as long as n is relatively big. And again, how big n has to be kind of depends on some hand waving and depends on how weird your population is. But usually for n's bigger than 10 or so, this is a reasonable assumption. Um, and we're assuming that our sample is an unbiased random sample of scale measurements. And so what the t-test is, and this is, for example, what the t-test function does in R, is to calculate the sample mean, x bar, and sample standard deviation, s. So again, these are things we're computing. These are like descriptive stats we're computing on our sample. Then we're computing the sample standard error just by dividing s by the square root of n. And then we can compute this t-score, which is how many of these standard errors away from our null hypothesis are we. We pick which t-distribution we're going to use by computing the degrees of freedom, which is n minus 1. And then it's going to compute for us, right, how much of the t-distribution is even more extreme than we are. And so this could be, again, a one-tailed test or a two-tailed test, depending on what our hypothesis is. Sort of the default thing to do is a two-tailed test, unless you really have a strong hypothesis ahead of time about what direction you care about. So again, in practice, you wouldn't actually do these steps. You just let R do them for you. Right in the lab, you're going to do it both ways, both sort of doing these steps by hand as well as using the t-test. And so this is the assumptions we're making here are not always perfect, right? Especially this first assumption, but these are generally true enough that the t-test, it makes the t-test pretty widely applicable. This is probably by far the most common statistical test that people use, right? It doesn't require us to really know anything about the population, except for specifying this null hypothesis mean, right? What we, which again is usually either 0 or in our beer example, this was like 45, for example, right, which is our baseline IBU. All right. Any questions about any of these steps? Okay. So one concept that's going to come up if you actually, for example, try to use a t-table is that the critical t-value that we talk about is that this is a value at which we would reject the null hypothesis. And so for a normal distribution, for example, if we are going to do a two-tailed test at an alpha level of 0.05, then this critical z value is 1.96. Right, so what that means is that if we obtain a z-score that's either bigger than 1.96 or less than negative 1.96, then we would reject the null hypothesis. That's kind of our critical threshold for saying we think this sample is not coming from this null distribution. Now, for the t-distribution, remember the shape of this depends on these degrees of freedom. It depends on how big the sample is. And so where this critical value is actually going to depend on the size of our sample. Right? So if we have an infinitely big sample, it'll be 1.96. But if we have smaller samples, it's going to be a larger number than 1.96. And so, again, this is sort of pre-computers. This was the only way to do this, was looking up in these tables. And so the columns to care about here really are like these last two. And so this very last one, for example, is the two-tailed test with an alpha of 0.05. And so what these numbers in this column are the critical t-values for each of these degrees of freedom. And so what this says is that if you have 1 degree of freedom, meaning that you have a data set of exactly 2 data points, the critical t-value is 12.71. Right, what this means is that if you only collect 2 samples, you need to get a t-score of at least 12.7 in order for you to reject the null hypothesis. This is a very big number, right? And so what this means is that if you only have 2 samples, both of them need to be really far away from your null hypothesis in order for you to say that this is actually that you think that this sample is not coming from the null, right? And so remember, what's going into this t here is both your distance from your null hypothesis and this thing down here that depends on uh, the sample standard deviation in your data, right? So if your data points are kind of variable or relatively close to the mean, this t-value is going to be lower. And so you can see as the degrees of freedom go up, meaning as your sample gets bigger, this critical t-value starts getting smaller and smaller. Right, for this column here, this is a one-tailed test of 0.05, which is the same as a two-tailed test of 0.10. The t-values are smaller here, right? That if you're doing a one-tailed test, this critical value is smaller. But still, both of these are sort of slowly getting lower. This right-hand column here will eventually get down to 1.96 for big enough sample sizes, right? But so this critical t here again is changing because the shape of the t distribution is changing with our sample size. Another thing we could use these critical t-values for is for making confidence intervals. So the same kind of logic we were doing with the normal distribution, right? That these critical values tell you the sort of upper limit of how many standard errors away we would expect to be from wherever the true population mean is. And so we can get a 95% confidence interval, very similar to the way we were doing it with the normal distributions here, by just taking this standard error. Again, in this case, this is the standard error we're measuring based on our sample standard deviation, and then multiplying by this critical t-value. And so since these critical t-values depend on the sample size, that means that the size of our confidence interval is actually going to depend on our sample in two different ways, right? So this standard error depends on our sample size because it has that square root of n in the denominator. And this critical t-value depends on our sample size because the t distribution is changing its shape depending on the size of our sample, right? So it used to be that when we were doing stuff with the normal distribution, this critical value was a constant, which was like 1.96, for example, whereas this sampling error of the mean was getting smaller with bigger samples. Now both of these values are changing. Right, they're both changing in the same direction, which is that as our sample gets bigger, this confidence interval is going to get smaller. Right, so another way you can think about what's happening here is that for small samples, our confidence interval gets like extra large, larger than it should be for a normal distribution, because there's all this extra uncertainty about whether we actually measured this sample standard deviation well or not, right? Whether that sample standard deviation is actually a good measure of the population or not. Because there's that extra uncertainty, we need to make our confidence interval extra big for small sample sizes. All right. Again, feel free to ask questions at any point. I can always, even if it's a couple slides back, I can always go back. Okay, so we've been talking so far about t-tests of a single population, right, where we are taking samples from some population and testing against some null hypothesis value. Another way we might use t-tests is for detecting changes. So for example, we are measuring two different values from a subject, and we want to test whether those measurements are different or not. And so the way we're going to think about this is by what we want to do is test whether the change in those measurements is different from zero. And so when we use a t-test in this way, it's called a paired t-test. The test itself is completely identical to the test we just talked about. The only difference here is that instead of using the raw data we're collecting, we instead take this within person difference. And then we're going to subject these different scores to a t-test. And in this case, it's almost always the case that our null hypothesis is zero. There might be cases where you have some kind of control condition and you want to and you have some sort of baseline amount of change. But usually what we're looking for here is whether there's any difference in these two measurements we're getting from each person. And so all we do is we take the difference between these two measurements and then are doing a t-test on these different scores. And so you could kind of think about it as we're just creating a new data set, right? We're taking our old data set where we have these two values per person, and we're creating a new data set with one number per person, which is the difference between their measurements. Um, Also, it's important here to note that n, right, for determining our degrees of freedom, is the number of these difference scores, which is the number of participants. So it's not the number of observations, which is 2 times the number of people, right? The n here is the number of difference scores, which is just 1 per person. So, for example, let's say we're interested in whether caffeine has some impact on physical activity. We could take some Columbia students who normally drink a lot of coffee each day. We're going to measure how many steps they take per day using a pedometer. And so we get a first measurement for each student. So we get 8 numbers on the first day, which is for each student, we count how many steps they're taking. Then we ask them not to drink any coffee for a week. And then we get a second set of 8 measurements of their steps on day 8. And so, right, what we want to figure out here is whether caffeine had any impact on or caused any kind of change on their number of steps on this first day versus this week without caffeine. Um, right, and so the question is, how would we use a t-test to test this, right? What might our hypothesis be? What's our null hypothesis in this case? So feel free to use the chat for some ideas. Uh, right, what would be the null? What would be the should this be a one-tailed test or a two-tailed test? Um, right, and what we have 16 numbers that we got. We got 8 on the first day, 8 on the second day. Sorry, 8 on the first day, 8 on day 8. Um, what numbers would we actually put into our t-test? Yeah, so there's a good question in the chat about the sample sizes here, right? So for this kind of paired measurements where we're getting 2 measurements from each person, um, the sample size here is just the number of people, right? And so uh, that sort of can't change from time point to time point, right? Because we're assuming here that we're getting exactly 2 measurements from every single person. Um, so we're going to talk in a second about cases where that's not true, right? But at least for this kind of paired test, uh, we're assuming that we're getting a complete measurement set from every person, and so the sample size here is just the number of people. So the null here is that there's going to be no change between the groups, right? So the null hypothesis is that these difference scores should be centered around 0, right? They're not going to be exactly 0. Some people are going to walk a little more, some people are going to walk a little less. But that sample mean of the differences should be centered around 0. Uh, and so what we could do is take these difference scores and put them in a t-test, right? And then so we can compute a t-score, which is uh, compute the mean of the differences and see how far away it is from 0, right? In these by giving a t-score, which is how far away is this mean from 0 divided by our standard error that we've estimated from our sample. So what about then we want to compare this t-score to our t-distribution. Should we be doing a one-tailed test here or a two-tailed test? Should we be looking at t-scores that are only in one direction or under both of the tails of the curve? Yeah, so we probably want to do a two-tailed test here. It depends exactly what we're testing, but um, most likely we'd be interested in changes in either direction, right? It might be that lowering caffeine is making people increase physical activity, or maybe it's making them sluggish and doing less physical activity, right? At least before we see the data, if we don't have a strong hypothesis about the direction, we should be doing a two-tailed test, right? So what we could do again is we could look at uh, we so one thing, if we're just interested in rejecting the null hypothesis or not, we can look up for a sample size of 8 people, which again is degrees of freedom of 7. Figure out from a table, for example, what's a critical t-value. How big would our t-value have to get, either positive or negative, in order to reject this null hypothesis at an alpha value of 0.05. Okay, so right, the idea of the logic with these difference scores is that um, instead of putting in the actual data we get, we instead compute this difference between the first and second times, and that our hypotheses are about these differences, not about the actual absolute value of steps that people are doing. Right. So, for example, if we have one student that walks 6,000 steps and another that walks 9,000 steps at the beginning of the week, and then after the week, student one is now walking 6,100 steps, student two is walking 9,100 steps. Those would both be the same difference score, right? Our hypothesis here is that there's going to be, we're interested in whether there's a change in people's walking. Our hypothesis doesn't say anything about what just the baseline amount of walking is. Um, and so the idea here is that we're assuming that there's some kind of additive effect, right? The hypothesis here is that if there is some kind of change in the population, that's going to be an additive change for every person, right? That if we're getting a confidence interval for example, that's an interval about how much change there is from the second day versus the first day. And so this additive effect assumption may or may not be a reasonable one, right? It depends on uh, it depends on what you're measuring, right? For steps, it is maybe not totally unreasonable, although you might think that if someone was walking like 100 steps and they went up by 100, that's maybe a bigger difference than someone that's already walking 10,000 steps. But with these difference scores, again, we're just canceling out those baseline individual differences. Um, yeah, there's a question about when we would use a one-tailed test here, right? And yeah, it would really only be appropriate to use a one-tailed test if we had a specific hypothesis about what direction this was going to change, and that we wouldn't be interested at all in the other direction. Uh, so in this case, it might be a little harder to justify a one-tailed hypothesis unless maybe from prior work we have some very strong hypothesis about this. I don't know, but uh, right, that the idea here, you should only do the one-tailed test if you think a change in the other direction, like, would it be a publishable result, right? That it would be a sort of meaningless result that's not interesting. If the other direction is potentially interesting, then you'd want to do a two-tailed test, right? That basically ensures that your false positive rate is still what it's supposed to be, which is 0.05. If you picked your one-tailed test, depending on what direction your data turned out, you're effectively going to double your false positive rate because you're only counting the area under the curve that went in the right direction, right? Which is not what we should be doing. Okay, so there's another situation where instead of getting multiple measurements from the same people, we're actually getting measurements from different groups of people. Um, and so the paired t-test we talked about is basically just the same as the single population t-test, right? We're just doing it on differences instead of on an individual measurement. Uh, but this situation doesn't really work for two different distributions, right? So, for example, say we want to ask whether there's a significant difference in family income in among families in two different states, for example. Uh, and so here, this is not like a paired t-test, right? That there's no obvious way to like pair up the families and to get a difference score, right? These are just two different groups. Um, we wouldn't know which ones to pair up, and I mean it might also be the case that the groups are different sizes, for example, right? So there's not going to be any way to pair them up. Um, yeah, there's also a question on chat about the one-tailed test here that people often want to use one-tailed tests because it'll be easier to get significant results, right? For example, if you look back at the t-test table, the critical t-values are smaller for the one-tailed test than the two-tailed one. Um, right, and the reason for that is that we're only caring about the area under one of the tails. Um, right, but again, it's really only it's sort of more sensitive test if we really only care about one direction. Um, but if either direction is interesting, then it's kind of overly sensitive, meaning that our chance of a false positive is higher. Okay, so we need to basically figure out a new way to do null hypothesis testing in this case where we are, excuse me, um, where we have two different groups instead of this single group with a single mean. So we basically need to figure out some kind of way of getting a sample measure that gives a single measure for these two distributions. Okay, so let's imagine we have some data here, which is that we we have people drinking coffee and people drinking tea. We're measuring how fast they're completing a puzzle. But what we want to know is whether the coffee drinkers are finishing this puzzle faster than the tea drinkers, right? So our null hypothesis here is that these distributions of reaction times are the same between the two groups. So what we want to do is find a way to get a single number from this data set that measures something about how big this effect is, right? How big of a difference are we seeing in our data between these two groups? And then we want to ask how that effect size would look if the null were true. And then we can see whether the effect that we're getting in our data is surprising or not, assuming that null is true. Right, so the null hypothesis approach here is basically the same idea, right? We want to get a null hypothesis distribution, and then we need to figure out what the sampling distribution of that measure is going to look like in this more complicated case. Okay, so the null hypothesis here is that these two groups have the same mean, right? Meaning that the time it takes the tea drinkers and the coffee drinkers to complete the puzzle is the same. And so the kind of simple measure of effect size here is simply just taking the difference in the means between these two groups. Right? We can ask how fast on average did the puzzle drinkers solve the puzzle. Excuse me, how fast on average did the tea drinker solve the puzzle? How fast on average did the coffee drinker solve the puzzle? And so what we want to do is figure out like what the null distribution of this effect looks like, and we want to figure out a way to get a t-score from this. And so the numerator of the t-score is that we need to compare our effect to the null effect, and so that's pretty easy, right? Which is that the null effect here is that the means should be the same. And so, yeah, so there was just a question in chat here too about, right, how do we figure out what the null is? And so, again, in a lot of cases, we're comparing to a null of 0, right, which is that the null is that the mean time should be exactly the same. Again, there might be cases where that's not true. You might want to compare to like some kind of placebo condition, maybe, or but at least in this example, right, the sort of obvious mean is that the obvious null mean is 0. So yeah, and again, this will depend on the experiment, but usually that the mean of the null distribution is something it's not coming from the data, it's coming from some kind of hypothesis, some kind of theory that you have about what's going on. So the null is usually pretty easy to pick. the null mean. The problem is we need to get a t-score, we need to divide by some kind of standard error term. Um, and so this one is the one that's like not, it's not immediately clear how to do this, right? The way we did this before was uh, calculate the standard distribution, the standard deviation, and divide by the square root of n. um, so here it's not really clear what the standard deviation should be for this because there's two different distributions. It's also not really clear what n should be here, right? Because we have two different n's in our two different data sets. So it turns out that if you add or subtract two random variables, the variances of those variables actually add. We're going to talk about this a lot more when we talk about ANOVAs next. But what that means for our case, so let's just, in this example, the number of coffee and tea drinkers is the same. And we're also going to make this assumption that whatever the population distributions of these things are, the variances are equal. We're going to come back to this assumption in a second, but this at least is the like traditional assumption to make here. And so at least under these assumptions, we get this relatively simple formula for the standard error of this difference score, which is that we just take the variance of our coffee drinkers, we add it to the variance of our tea drinkers, and then we take the square root of that and divide by the square root of n. And so this is called a pooled variance or a pooled standard deviation, right? And the pooling here basically just means that we're adding up the variances for the two groups. Right, one thing to note here is that the n in the denominator is the size of each group. This formula only works if the groups have the same size. Right, and so again, all of these things are things we can compute easily from our data set, right? We just compute standard deviation of coffee, square that, standard deviation of tea squared, add these up, divide by the size of each of the groups, then take the square root of all of that. Right, and so in this particular case, at least, right, we can now get our t statistic, right, which is that we take the mean of one group minus the mean of the other group. That gives us our kind of size of the effect, right? How big of a difference is there between groups? We compare that to some null hypothesis about the mean between the groups, which again is usually, so this part is usually 0. And then we can divide by this kind of pooled standard error, which again, at least in this case that we've been talking about, is just we can just use this simple formula here by just adding up the variances of the two groups, taking the square root and dividing by the square root of n. So one other thing, if we want to actually do this test, right, what's something else we need to know in order to actually get a p-value out of this? So we have our t-score, right? We have our t-score. If we want to convert our t-score into a p-value, what else do we need to know? Yes, while you're thinking about that question, again, think about what else we need to know here in order to get a p-value. Yeah, there's a question about this formula. So we're going to, in the next few slides, we're going to go through more complicated versions of this formula. This one is the sort of simplest case, which is that both of our groups have the same exact size, which is this n. So if we have 10 people that drank coffee and 10 people that drank tea, then n would be 10 here, right? Not 20, not the total number of people, the number of people in each group. So this equation only works if the number of people in each group is the same. And it also is making this extra assumption that the variances of these two groups are equal, right? We don't have to know what they are. It's just making the assumption that the variability among coffee drinkers and the variability among tea drinkers is the same. So under those, right, in this restricted case, we have this nice simple formula here. Okay, so we're almost ready to get a p-value, right? But there's still one thing we're missing here. So we have a t-score, and to convert this t-score to a p-value, we're going to need to look at something like an area under the curve, right? So what's the last thing we need here in order to, aside from the t-score, there's one other thing we need to know to use a t-distribution to get a p-value. So remember that there isn't actually one t distribution, right? There's actually many t distributions. So we need to figure out which t distribution we're going to use here. Yeah, that's right. So it's degrees of freedom, right? So we want to uh, we need to figure out which t distribution we're going to use here, right? How heavy should the tails be? How close should this be to a normal distribution versus having these heavy tails? And so in this case, the degrees of freedom formula looks like this, which is you add up uh, the number of samples in each group and subtract two. And so you can sort of think about this as like uh, there's two different means here, right? So we know two numbers. We know the mean of one. We know the mean of the other. So there's sort of two things that we're specifying in our t-score. And then this is the total number of data points that we have, right? So the degrees of freedom here is the total number of data points. So the number of coffee drinkers plus the number of tea drinkers minus two, because we've already specified two of the means in this t-score. Um, so it's already, yeah, that's right. And then, yeah, another way to think about this, like let's just say in the chat, is that you could just think about this as kind of like the degrees of freedom for each mean separately, right? So n minus one for the coffee drinkers, n minus one for the tea drinkers, and just add those two together. Um, okay, so if we have this situation where we have two groups that are the same size, um, and we're making this assumption of equal population variances, then this is all we need to know, right? So we compute this t-score. This stuff is all from the data. This stuff is coming from our hypothesis, and it's almost always going to be zero. This we can compute from our data. Once we have this t-score and our degrees of freedom, we can then compute the area under the curve, right? Either using like the integrate function or using a t-test or something like the t-test function, something like that. Um, okay, but so what about other situations? And a very common one, for example, right, is that the number of people in these two groups is not the same, right? So what if the number of coffee drinkers is not the same as the number of tea drinkers in our sample? Um, in this case, we have this super ugly formula we have to use. Right, you don't have to memorize this. Uh, the reason it's so ugly is because it's computing a weighted sum. Um, the way you can think about this is that we're trying to do the best job we can of estimating what the true population variance is. And here we're assuming that it's the same in these two groups. And so the bigger group is going to give us a better estimate of the population variance. And so we want to have an equation like this where you can see the estimated variance from the coffee group is getting weighted based on the size of the coffee group. And the estimated variance from oops, that should be T, that's a typo there, from the T group here should be weighted by the size of the T group, right? And so what this means is that the bigger group is going to get a bigger vote in what this population variance is. And then there's all these other sort of weird weighting terms here, right? And so, again, this is kind of a messy equation, but it's not, we know all the things in here, right? It just, all we need to know is the size of each group and the variance in each group in order to compute this. Right, what it's trying to do is give us a better estimate of this population variance by giving a larger weight to the bigger sample. This formula works if NC and NT are the same, right? So if they're the same, then actually you can sort of work this out. But like what'll end up happening is that these first terms will cancel, and you'll end up with the same equation that we had before, right? So this is the sort of general form for computing this standard error across two groups when and the groups might be different sizes. Um, okay, before we get to the last part, any questions about this? So again, once we compute the standard error, that lets us compute a t-score, and then once if we have that t-score and the degrees of freedom, we can compute a p-value for this t-test. being equal. And so for a long time, people just lived with this assumption, right? We just are making this assumption that whatever the population distribution of these two groups is, it's the same. Um, but the problem is that this might not always be true, right? That uh, so in the example we were talking about, right, maybe there's like some kind of extra variability in our coffee group where some people are really sensitive to coffee, and so they're going to show a big change. Um, and right, and kind of just in general, we like our conclusions to rely on as few assumptions as possible, right? That every time we add these extra assumptions, it means that if that assumption is not true, then the p-value we're computing is not really right, right? It's based on a version of the world that doesn't exist, and it might not be good for actually making decisions about what we're seeing in our samples. And so the good news is that you don't have to make this assumption of equal variances. Um, the bad news is that it's a little complicated, and we won't ever have you do this by hand, but you can ask R to do this test for you. So to do it with this, where you don't make this assumption about equal variances, um, you start by computing this kind of pooled standard error. So you just take the variance in each group, divide by the number of people in that group, add those things together, and take the square root. The t-score formula is exactly the same, right? We just take the difference between our means, compare it to some null difference, and divide by our standard error. So that's all easy enough to do. Right, but remember, we still need one last thing, which is the degrees of freedom. And so the degrees of freedom in this case, where we don't make the assumption that the variances are the same, the degrees of freedom actually comes from this equation, which again we'll never actually ask you to use, and it's right. So obviously, so first of all, it's like very weird. It looks very weird, and it's also going to give numbers that are not integers, right? Which is one reason why, like pre-computers, this was a hard thing to deal with because it means you can't really use the t-test tables to do this. Um, I just put this equation up here not because you actually have to know it, but just to give you a sense that there is a way to compute the degrees of freedom. It depends on the variances of each group and the size of each group, but they're mixed together in this very complicated way. Um, again, the only way we'll actually ask you to do this is in R. So if you run the t-test in R, one of the arguments to that function is it's going to ask you, do you want to assume that the population variances are the same or assume that the population variances are different? If you tell it that you want to assume that they're different, then it'll compute this degrees of freedom thing for you, right, and construct the t-distribution that has this exact number of degrees of freedom, which is going to be some like decimal value. Okay, so any questions on this? So right, we've talked about basically maybe about 4 different sort of versions of the t-test that they all are very similar in the sense that they all are you're measuring something in your sample. You're taking that measurement so you're measuring something in your sample. You're comparing that measurement to some kind of null hypothesis and dividing by some measure of standard error, right? And so you could be measuring from a single population. That's the one sample t-test, meaning that you're taking samples from one population. It could be a paired t-test, meaning that you have some hypothesis about differences within a person. Or it could be one of these two sample or independent sample t-tests, which means that you're taking measurements from 2 unpaired groups, and then you want to compare the means of these 2 groups. And again, the exact formulas you use in this independent samples case depends on whether or not the groups are the same size, and it also depends on whether you want to make this assumption about the variances being the same or not. All right. Any questions about any of those? Sure. Yes. Yeah, so there's a question about degrees of freedom, and so In this particular case, the degrees of freedom um, is uh, basically it's controlling the shape of our distribution. So smaller our degrees of freedom, the more weird this t-test looks. Meaning, uh, right? So in this case, right, this is a t-distribution with 3 degrees of freedom. For a t-test, the degrees of freedom is just n minus 1, right? So this is a t-test with 3 degrees of freedom, which basically means that its tails are much heavier than a normal distribution. Right, the fact that there's 3 degrees of freedom is basically saying that uh, so we measured 4 things in our data, and to compute the t-score, we computed the mean, and we used that mean in the t-score. And so uh, there's sort of like 3 other things in the data we haven't used yet. Right? We computed the mean, that sort of used up like 1 degree of freedom in our data. So now we're down to 3. And there's only 3 things. There's like 3 extra degrees of freedom in our data that we haven't used yet, which is not that many, right? And so what it means is that uh, our data set is like pretty small and uncertain, and so having low degrees of freedom means that our t-test also needs to be kind of uncertain. It might be that we really badly misestimated the population variance here because our data set is so tiny. Um, as our data set gets bigger, the degrees of freedom get bigger, right? Meaning that if I just tell you the mean for a data set of 64 data points, there's still like 63 things you don't know, right? There's still, that tells you very little about where the actual data points are. And so that corresponds to a data set where there's like lots of information, and our estimate of the population variance is hopefully a lot better, right? And so, uh, right, at least in this particular case, right, degrees of freedom is changing the shape of this curve. This is going to come up in other. Part of the reason that I'm starting to talk about this in this lecture is because this degrees of freedom idea is going to come up in other distributions as well. Right, you can think about it as it's kind of a parameter of this distribution that depends on the size of the data set. Okay, let's get back to where we were here. Okay, so the last thing I want to talk about was just this is a more general point, which is not just about the t-test, but is a more general point about these kinds of statistical tests in general, which is that there's often a trade-off between making assumptions in our test and the power of our test, meaning how sensitive our test is of detecting interesting things in the world. And so, in like the coffee tea example I was just showing you, if you assume that the variances of the 2 groups are the same, you get a p-value of 0.158. If you don't make this assumption, it doesn't change things that much, but it does raise your p-value by a tiny amount. Um, and so this is sort of generally true that as you take away assumptions in your test, it's going to make your p-values be bigger. You can think about one-tailed versus two-tailed tests as kind of like this too, right? Like, so a one-tailed test is making this extra assumption about our data that it's only could change in one direction. So when we make that extra assumption, it makes our p-value smaller, which is a good thing because we want our power to be high, right? What we want is that if the null is actually false, we want to have a good chance of actually knowing that it's false, right? We want to get that true positive result instead of a false negative. Um, but we also and so yeah, and again, the power here is controlled both by our assumptions as well as alpha, right, which is our chance of accepting the null. And so we want our false positive rate to be low, meaning that if the null is not true, that if the null is true, we don't say we have a positive result. We want our power to be high, meaning that if the null is false, we can actually detect it. And so assumptions help us here, right? Assumptions make our power stronger. So if we can make some assumptions that actually correspond to what's really happening in the world, it's not going to hurt our false positive rate at all, but it will increase our power, which is a good thing. The problem is that making assumptions only works if those assumptions are true or at least close to being true, right? And so if we're making assumptions that are not true, then the p-value we're getting out doesn't really mean much of anything, right? The p-value we're getting out is talking about a sort of null world with assumptions in it that doesn't actually correspond to our real world. And so the p-value is not super relevant for making decisions in the real world where we live. Um, so there's basically this trade-off, and this is the kind of thing that people within a field will often argue about what the right assumptions are to make. There's no general answer to this. It basically just depends on what kind of things you're willing to assume are true. And so, uh, right, the p-values here that we're getting are when we get a p-value, we're basically assuming that the null is true, and we're also making some extra assumptions usually. So we're making extra assumptions like we're almost always making the assumption that our samples are like unbiased random samples from the population, for example. Um, and in the equal variances t-test, we're making this extra assumption that the variances in the two groups are equal, right? And so if those assumptions are correct, then that's a good thing, that it's going to make our test more sensitive. If those assumptions are wrong, then it means that we're computing p-values in a world that like definitely doesn't exist. And so it's not wrong exactly. It just depends on assumptions that aren't true, and so it's not going to be very useful for making decisions in our real world. Um, and again, there's this trade-off. If we want to take away those assumptions, it makes it more likely that this test is actually relevant to us, but the test is going to be less sensitive. So there's a bunch of extra slides in the PDF version of this that's on coursework. So if you're interested, I showed some examples of this, of like using both t-tests as well as things like permutation tests. So permutation tests make fewer assumptions about our data, and so when so if those assumptions that we're making in the t-test are wrong, then the permutation test will be better. If the assumption tests that we're making the t-test are right, then t-tests will be better than permutation tests because they'll be extra sensitive. So again, you can look through those if you want. The important thing really is just this general idea that we have this trade-off we have to make, and we really have to use some kind of knowledge about the thing we're studying to know where a good setting of that is. Okay, so just to sum up, right, we can use this t-test as one of the sort of practical outcomes we can finally use after we've been talking about all these probability things. And so we could use this to capture, we could use this for a single distribution, or we could use this to capture differences between independent samples. We could, again, have this choice of computing, of assuming equal or different variances in the groups. In either case, we're going to get this p-value out, which is testing whether this null hypothesis of whether the means are the same or not in the two groups. There's this general trade-off between power and generality about how we want to set these assumptions. Right, so yeah, there's a question about alpha versus p, right? So alpha is something that we're setting before we see the data, which is what's going to be our threshold for rejecting the null hypothesis. So how weird does this data have to look for us to think that it's not coming from this null distribution? And then the p-value is what we're actually computing from the data, right? Using the data, we get this p-value that tells us how weird is this data, assuming the null hypothesis is true. And so if our p-value from the data is 0.01 or something, we can compare that to our alpha threshold. And if the p is less than our alpha threshold, then we'd say that this data set is not coming from the null, right? That we'd reject the null hypothesis, right? So the alpha is something that we're setting in like our setup of the test. It doesn't depend on the data, right? It's something that we're setting before we ever see the data. The p-value and the alpha is basically controlling this overall false positive rate. So how willing are we to make a mistake, right? And then the p-value is something that's for this particular data set. And if the p-value is small, then if it's smaller than our alpha, we're going to say the chance of a false positive is low here. We're going to say that this is a real result. All right, we're about out of time. Again, if you had any problems with the stream besides my coughing fits, let me know if there are any technical issues. If you have additional questions, you could ask at the TAs the labs tonight. You could also set up a Zoom session with me to talk about things. And yeah, I'll plan on seeing everybody. The next lecture will be
in 12 days on the 20 on Tuesday the 24th.